In this podcast, we're just going to finish looking at proving whether a triangle is a right triangle or an isosceles right triangle. All right, so proving a triangle is a right triangle. All right, so we have to make sure that Pythagorean theorem holds. In your notes, I want you to underline that we're going to calculate the distances of all three sides and test Pythagorean theorem. Okay, so if Pythagorean theorem holds, we know we have a right triangle. All right, so we're going to prove that polygon with coordinates A at 1, 1, B at 4, 5, and C at 4, 1 is a right triangle. Right? All right, so first thing we have to do is always graph our figure. Second thing we're going to do is we want to state what we want to show. So we want to show the side measures satisfy Pythagorean theorem. The formulas we're going to use are the distance formula and Pythagorean theorem. All right, so two of our lines are vertical or horizontal, and we can just calculate the difference in the x-coordinates for the horizontal side and calculate the difference in the y-coordinates for the vertical side. For that diagonal AB, we're going to use the distance formula. All right, so the length of AC is just the difference between the coordinates, between the x-coordinates, because it's a horizontal line. So the difference between 1 and 4 is 3, and the absolute value of that -3 is 3. BC is the difference between 5 and 1, so that's going to be the absolute value of 4, or 4. And then using the distance formula, we have the difference in the x-coordinates. Right, so our two x-coordinates for AC AB are 1 and 4, so we have 4 minus 1 squared, and then the difference in the y-coordinates, 5 minus 1 squared. Notice that whatever point we start with for x, we start with that point for y. So 4 minus 1 is going to give us 3 squared. 5 minus 1 is going to give us 4 squared, and that would be square root of 9 plus 16, which is the square root of 25, or 5. Right, and then we tested Pythagorean theorem. All right, so one leg was 3, one leg was 4, and the other side was 5. We don't know it's a hypotenuse until we show that Pythagorean theorem holds. So we have 3 squared plus 4 squared equals 5 squared. That would be 9 plus 16 equals 25, or 25 equals 25. So since the sides of triangle ABC satisfy Pythagorean theorem, triangle ABC is a right triangle. Okay? And so we've proven that this is a right triangle. Okay? All right, so if you have any questions about this problem, you can always ask in class, and we can go over it again. All right, we're going to look at another problem. All right, and this is, we want to not only calculate, not only figure out if this is a right triangle, we want to figure out if it's an isosceles right triangle. Of course, we're not going to have to really do any additional work, because we're just going to use the distance formula again, and with that we can show whether it is an isosceles right triangle. I'm trying to make sure I can get everything in here. Even though you have it in your notes, I want you to be able to see it. So the last proof I did as a very short paragraph proof, because it was pretty straightforward. As long as we have all of our work to go with it. This one I did as a 2-column proof. Right, and I'm going to scroll down a little bit. First, I'm going to have you underline something in your notes. So in your notes, we're going to calculate the distances of the 3 sides. We're going to show 2 sides congruent. And then we're going to test Pythagorean theorem. All right, so those are the things we're going to do in this particular proof. Pretty much like the other proof, except we have to check to make sure we have 2 congruent sides. I'm going to just scroll a little bit, and that's actually what we're going to be showing. Actually, I'm going to write that again for us down here. I almost got the whole proof in. Let's go a little bit farther. There we go. Almost. There we go. We got everybody. All right, so we're going to prove that polygon with coordinates A at 4, 1, B at 5, 6. My recording screen is blocking me, and C at 1, 3 is an isosceles right triangle. Okay? So I'm just going to add one thing to your notes, a kind of rote show next to what we want to prove. All right, so we're going to show, and maybe add this to your notes somewhere. You can write it right where I'm writing it. So there we go. Show that we have two congruent sides and that Pythagorean theorem holds. We'll abbreviate Pythagorean theorem. Okay. All right, so that's what we're going to be showing. All right, we've got our figure graph, which is always step 1. Step 2, we figured out what we want to show. And so the formulas we need for that are the distance formula and Pythagorean theorem. Here we have one side. No, all of our sides, I'm sorry, when I looked at that, I thought we had a vertical line. All of our sides we have to use the distance formula with. We have no horizontal or vertical sides. All right, so AB, we take the difference in the x-coordinates, 4 minus 5 squared, plus the difference of the y-coordinates, negative 1 minus 6 squared. That's going to give us 1 squared. Actually, negative 1 squared, but it really doesn't make a difference. It's going to be positive anyway. Negative 1 squared plus a negative 7 squared, which gives us 1 plus 49, which is the square root of 50, which simplifies to 5 square roots of 2. Got a little grip in the board there. You can see probably looks a little wavy. If you weren't sure how to calculate that was 5 square roots of 2, we have 50. And 50 is divisible by 2. And that gives us 2 and 25. 25 is 5 times 5. So 1 5 comes out, 1 5 goes away, 2 is left in the radical. So that's why it's 5 square roots of 2. All right, so BC is the difference in the x-coordinates, 5 minus 1 squared, plus the difference in the y-coordinates, 6 minus 3 squared, which gives us 4 squared plus 3 squared. And that would be square root is 16 plus 9, which is the square root of 25, which is 5. All right, so now last side, CA is equal to 4 minus 1 squared plus negative 1 minus 3 squared, those difference in those x-coordinates plus the difference in the y-coordinates. 4 minus 1 is 3, so that's 3 squared plus a negative 4 squared, which is 9 plus 16, which is the square root of 25, which is 5. So we see this is definitely an isosceles triangle. We have two sides congruent. By the way, this was left up. I had this up from before. We didn't know this was true until we used the distance formula to show that's true. Now we know that these two sides are congruent, but we didn't know those two sides were congruent before we did the proof. All right, so we have almost all the information we need. We have to figure out if, first of all, I mean, this is an isosceles triangle, but is it a right isosceles triangle? Right, so we have to use Pythagorean theorem and see that Pythagorean theorem holds. Right, so the larger side has to be our hypotenuse. Right, if this is a right triangle, it's 5 square roots of 2. That must be the hypotenuse. Right, so and the other two sides would be legs. So we have 5 squared plus 5 squared equals 5 times the square root of 2 squared. 5 squared is 25, so we have 25 plus 25 equals. And when you have a number outside the radical, you're going to square the number and square the radical. You're going to square the whole product. Right? So 5 squared would give us 25. Square root of 2 squared would be, you can think of it two ways. You can think of it as the square root of 4, which is 2. Or you can think of it as the square and square root canceling each other, and either way that's 2. So on the left side there we have 25 plus 25, which is 50. On the right side we have 25 times 2, which is 50, which means Pythagorean theorem holds. So I did this one as a 2-column proof. My first statement is triangle ABC, that is given. My next statement, AB is equal to 5 square roots of 2, BC is equal to 5, and CA is equal to 5. We know that because we use the distance formula. BC is congruent to CA because congruent segments have the same measure. Notice BC and CA are both 5. Therefore, we know triangle ABC is an isosceles triangle because a triangle with two sides congruent is isosceles. Right? That's what the definition of isosceles is. Isosceles triangle is you've got two sides congruent. Matter of fact, anything that's isosceles has two congruent sides, like the isosceles trapezoid. And then finally, triangle ABC is a right triangle, and we know that using Pythagorean theorem. So since Pythagorean theorem held true, this has to be not only an isosceles triangle, but a right triangle. Okay? So if you have any questions on this proof, just let me know. Really, it's an awful lot like the other proof, except we just had to state that we had two congruent sides. But in terms of the other steps, they were all the same. So just to review, steps to follow, so I didn't show every single proof I could possibly show you, but I showed you almost all of them. I showed you all of the ways to prove a parallelogram. I showed you the ways to prove a triangle, a rectangle, a rhombus, and a square. Right? I showed you all the ways for a rectangle and a rhombus. I didn't show you all the ways for the square because that would require me, mixing up every single possibility. But I showed you the most. I showed you the most common ones and the ones you'll probably use. And then I also showed you how to prove a figure was a right triangle or an isosceles triangle. And actually, in kind of a way, an equilateral triangle, right? If we just had one more side congruent on that isosceles triangle proof, that would have been an equilateral triangle. So our steps are, first we have to draw and label the graph. We're going to write down the geometric conditions that are required. What is it you want to show? You'll state the formulas that are used. You'll show all your work for the distance formula or the slope formula or the midpoint formula, whatever formula you're using. And then you'll have a concluding statement that what you've proven and why it's true. And that's going to be your paragraph proof. So it's really more than a statement unless you're going to write a very, very long sentence. It's going to be a paragraph proof or a 2-column proof. And I'll expect you to be able to do both, right? You switch back and forth just like I did. But if you just follow the steps that we've done in class, use your proof cheat sheet and use the information, the notes that you have on parallelograms and special parallelograms, you'll be just fine. And that concludes this podcast because that was the closing. Right? That's the end. So closings are posted. There is no closing for this particular Nearpod, but there will be some questions for you to answer. So if you have any questions, just ask me in class, and I hope you enjoyed this podcast. Have a nice day.